In this video, we'll talk some more about how circuits behave in the real world and one specific issue related to circuit behavior related to propagation delay. And then we'll also talk in this video about static logic hazards. So up to this point, when we've modeled our combinational circuits, say for example an inverter, the timing diagram for the inverter would look something like this. So when the input's low, the output's high. And when there was a change in the input, so here when x goes from 0 to 1, I see immediately the corresponding change on the output. In reality, there's going to be some propagation delay through this gate. So in reality, after the input changes, in this case going from low to high, after some delay, I'll see the output change, in this case going high to low. And the same thing again when the input changes from 1 to 0 after some delay, I'll see the output change. And so we would call this the propagation delay for this particular gate. Now note also in reality, the signals for this inverter wouldn't necessarily look like it's going straight from 1 to 0 or 0 to 1. In fact, there'd be a gradual discharging before it reaches 0, and we would say that once it reaches the 50% point of the halfway, we hit a 0. And the same thing again, when I go from low to high, there'd be a charging. Note also that these transitions, 1 to 0 or 0 to 1, these delays might be different for a particular set of devices and technology. Now this is important because the propagation delays are going to determine how fast I can run my circuit, or in other words, how fast or frequently I can put new inputs into my circuit. So say I had a combinational circuit, and I want to determine what's the maximum frequency that I can run this circuit, or in other words, put new inputs here on X, and then get the corresponding output Z. And in fact, this is going to be determined by the inverse of the longest path through this circuit. Or in other words, the greatest propagation delay through N, from the inputs, any of the inputs changing to any of the outputs. So as an example, let's say I had my full adder block. So I have the following implementation of a full adder, and I know that the gates, let's say an XOR, has a propagation delay of 4 nanoseconds, and an AND and OR gate have delays of 2 nanoseconds. So if you notice for this circuit, I have multiple paths through this circuit, from 3 different inputs to 2 different outputs. But the question when determining what's the maximum frequency I can run this circuit, or what's the which is the inverse of the longest path or the greatest propagation delay to the circuit. You can also think of this as the worst case delay through the circuit. So if I say that the inputs A, B change, I go through the XOR gate, which takes 4 nanoseconds, and then another XOR gate to the sum. So this path from A to B to the sum is in total 8 nanoseconds. What about from A and B to C out? Well, there's an AND gate and an OR gate, that's 4. But I also have a path through this XOR and then through this AND gate, which is 2 nanoseconds, and then the OR gate. So in total, this one has an 8 nanosecond delay, which is the same as the sum. So in this particular case, it worked out the worst case, or the longest delay for each of the outputs was the same. And so the maximum frequency is 1 over 8 nanoseconds, or 1 over 8 is 0.125, and nanoseconds is 10 to the negative 9. So I'm multiplying 0.125 times 10 to the 9, and the units for frequency are going to be in cycles per second, or hertz, and this is equivalent to 125 times 10 to the 6, and so I have 125 megahertz. So when looking at the performance of our circuit, or how fast we can run it, the frequency that we can use for our particular design, propagation delays are an important factor for determining that. The fact that gates have propagation delays can also cause other issues. So to see this, let's look at an example. So say I have the following circuit, two-level and/or circuit, and my inputs look something like this, A, B, and C. A and C are both constantly 1, but my B value changes after a given amount of time from high to low. And again, let's assume that all these gates, they have propagation delays. So the output of the inverter after B goes from high to low is going to take some delay before it actually changes and goes from low to high. The same thing for the output of this AND gate. After B goes from high to low, I'm going to see a change on the output of that first AND gate. Now the output of this second AND gate depends on B naught and C, the output of the inverter and the input C. So after this change, then I have to wait an additional delay before I see the output. So in this case, that output of the AND gate will be low until the output of the inverter, B naught here, goes from low to high. After some delay from that, then I'll see that AND gate go high. Now the output, F, is the OR of those two ANDs. And so the output is high. But after AB goes low, I see that actually it's going to drop low as well before the B naught C gate changes its state. And then the output F again goes high. This is an example of a glitch, because the values that my inputs were and how they changed, my output should have been constant the entire time. But because of these propagation delays and the input change, I actually saw a momentary change in my output. And this is exactly what a glitch is. A momentary change in my output. And this could happen multiple times, or like in this case, it goes low for a short period of time, then it goes high. Now, glitches can arise for different reasons, but one of the ways that we can protect against glitches is by identifying the conditions or the characteristics in a circuit which may result in a glitch. And these are called hazards. Now there's different types of hazards, but the specific hazard that we want to talk about are logic hazards, meaning that when a single input bit changes, I have the potential for a glitch. And we're also going to look specifically at a static logic hazard, meaning that the output should remain constant, as in our example above here, but didn't, because there's an easy way that we can prevent these static logic hazards. So the way that we can prevent a static logic hazard is by looking at the K-map. So for this particular function, I have f is equal to a and b, or b naught c. So this is my K-map for this particular function, and I see I have two product terms, two implicants, and the trick for identifying static logic hazards are whenever I have implicants, or these circles that are adjacent but don't overlap, this is a potential static logic hazard. And I can see that from here, when I changed from B to 0 to 1, we actually had a resulting glitch. To prevent this, all we have to do is include additional circle or implicant which overlaps any of the adjacent loops. So in this case, I would include the following loop, which is A and C. This will prevent the static logic hazards for this particular circuit. So in general, this is the process for eliminating static logic hazards. I identify any adjacent loops within my K-map and then include the overlapping loops.